So this is just like a few slides about some random stuff I thought might be interesting. It is a tad bit historical, but it should give you some interesting background and understanding how this space progresses. Okay, so the first one is if you look up the white paper, so not even the yellow paper, but the white paper and the original announcements about Ethereum, it is kind of clear that it was heavily inspired by Bitcoin, and more so the EVM itself, heavily inspired by Bitcoin script. And this actually gives you a background on why EVM is what it is like. It is a simple stack machine, and it has 256-bit stack items, which is a legacy coming from Bitcoin, where the main point of Bitcoin script is to validate signatures, basically. And that is the reason EVM is 256 bits as well. It seems like a good idea to keep it 256 bits in order to operate on hashes, signatures, etc. And if you look at one of the earlier versions of the white paper, which can be found on the Ethereum wiki on GitHub, I can put in links maybe later on the slides or just on the channel. But this is a copy from the original instruction set. And this first page doesn't actually look that much different to what it is today. But the second page has a few interesting opcodes which we really don't have today. And actually the screenshot is just too big and half of it is cut off. But these are the interesting ones here. You see all of these like ECMO, ECAD, EC sign, EC recover. These are not really instructions today. So basically, in the initial version, there were no precompiles. It was just really opcodes. And precompiles came about in an attempt to simplify the EVM, only leave the core instruction set in the EVM and somehow use some other kind of method to reach extended functionality. And that is what precompiles are. They supposed to be like special contracts which implement more complex functionality. And of course, what happens in reality is they are implemented in the client itself. There have been various attempts at to actually replace them with EVM code, to replace them with other means. None of this went beyond like proof of concepts or research. So they were really created to reduce complexity. But if you look at the various bugs and issues arising around precompiles, this doesn't seem to be the case. They are still like really risky constructs. Because we moved them out of the EVM, we kind of feel like they are not really part of the EVM. They are part of the system as a whole, but not really in the EVM. So they get like a different treatment, and they get overly complicated gas rules. And they also like rather inconsistent across each other, how they handle errors or various cases. There's really just no consistency across them. And then interestingly, Ketchuk really fits the bill of a precompile, right? Because it's a much more complex operation than everything else in the EVM. But somehow that actually stayed in the EVM because it was deemed to be too useful and too frequently used. And of course, one example is how do you actually do any kind of storage access or mappings? You would use some kind of hashing function, of course, Ketchuk in the EVM, in order to calculate like a storage location. So indeed, this decision was correct from the sense that it is a really frequently used opcode. Now, the next interesting part is gas prices generally. I'm not sure how many of you actually knew how gas prices are made up, because I think we can say that they are actually just made up. the initial set of gas prices, they were basically just a set of benchmarks on Pi Ethereum, which is an old Python implementation. It is not Pi-EVM, that's a different one. And that was a replacement of Pi Ethereum. But Pi Ethereum is like the original Python implementation. And I believe the gas prices were established through benchmarks conducted in Vitalik's laptop using Pi Ethereum. And there exist like various versions of Google spreadsheets with the results of these prices. I think they can be found in like all core dev notes. There may be links in there. It is really interesting, like historical artifact, just to see, where these come from. And of course, these gas prices underwent like frequent adjustments, over the past how many years, like 7 years. And here comes an interesting point, actually, with these adjustments. They're due to the fallout of the Shanghai attacks, which I suppose should have really included here. But the Shanghai attacks was a series of denial of service attacks on the network, where underpriced opcodes were utilized to basically slow down the network. And some of these opcodes included account creation and then self-destructing those accounts. But generally, they actually included making calls across different accounts. And as a fallout to that, there was one could say, an insane price change, how much a call was costing. I don't actually remember now the number, but it should be an EIP 150, 160. It went up tenfold. And as I mentioned, a lot of these heavy functions were moved out of the EVM into precompiles. And precompiles don't actually get a special treatment in terms of gas costs. You have to pay the same call cost, as you would have to pay calling any other account. And you would ask the question, what is actually this cost? What is this cost covering? The call cost itself. And the call cost mainly should cover the lookup of the account in the account tree, loading the account, and then execute just start of the execution. So some basic checks. And the account tree is actually multi-layered right now. So it's not like you would be able to, in one step, just look up if the account exists and what is the code of it. Rather, it may be 2 steps. So the top level tree itself contains, it is encoded as a tree, but if you decompose it, you would look at it as a map, where the key is the address, and the value is an array of various values, which includes the nonce of the account, it includes the balance of the account, and has a hash for the code, the code hash. It doesn't contain the code itself. It is only just the hash of the code. And then it also contains a storage subtree. And the hash of the code you can use then to look up the code in another mapping. So this is, of course, like an expensive operation to do because you may need to do 2 steps. And back in the day the Shanghai attacks took place, which was late 2016, and the changes, these repricings were happening early 2017. In those times, this is basically how clients operated. Now, since then, this has greatly improved, and it has been pioneered by Aragon. It is called the flat database model, where basically you don't actually try to, in memory and in storage, try to replicate the tree itself, and rather you store it in a flat manner, where you can actually just look up in one go all of these properties. You don't have to traverse the tree, you don't have to do anything like that. And the reason this tree model existed even in like the storage level initially, because whenever you do a modification, you need to recalculate, the hashes, because eventually you need to store the root hash in the block after any kind of modification. And if you store it in such a manner, then whenever you make a change, it's rather easy to recalculate. If you do it like in a flat database manner, then you need to have like a separate method, a separate process to actually recalculate all of this. Anyway, we went off quite a tangent here. But the point is that with these repricings, calls became like super expensive. And if we would have moved a Ketchak into a precompile initially, that would have also become super expensive. And maybe these repricings actually wouldn't have happened the way they have happened. And potentially, it would have been much harder to solve the DOS issues. Another interesting point on gas prices is lately, this was like the initial benchmarks which established the prices we have. But then after a certain time, there have been like certain instructions or certain precompiles which have served as benchmarks to which you would tune other precompiles. And one such case is the EC recover, which serves as kind of like a benchmark. So what this actually means is you would measure how much time it takes to run like an EC recover call, and then you would measure the opcode or precompile you want to maybe reprice. On the same machine, you would do these two measurements, and you would be able to then adjust the cost of the second precompile according to the EC recover. And we claim that the EC recover may be like a good baseline. There have been a bunch of interesting benchmarks which kind of confirm that EC recover may be like well priced across many of these other precompiles or instructions. And there have been a bunch of repricings. Notable ones include EC-add, EC-mul, EC-pairing. Those precompiles are used for elliptic curve operations. More importantly, they're used in all kinds of ZK constructs. Those have been repriced and partially, calculated against like EC recover. And at the time they were repriced, I think the cost dropped like 2 to 4x, which was significant, which basically made it possible to do useful ZK constructs on EVM. Another repricing which took place was like ModExp, which has a complicated story, and this can be looked up in all core dev notes. And then lastly, on gas prices, there are several papers on various attacks and mispricings on the EVM. And mostly under this, I think it really just talked about precompiles, because those were the ones which received repricings, as well as the calls. But the actual opcodes, all the basic like push opcodes, arithmetic, logic opcodes, they weren't really repriced. And various groups, including my group, have been doing benchmarks in finding the actual relatively good values for these operations. And it seems like there are some mispricings across them, but in many cases it's actually just priced much higher than they should be. So yeah, I do think that at some point the prices of a lot of the opcodes may be changing. This is a much simpler topic. The invalid opcode, which isn't actually an opcode, it is just an agreement that the FE byte will never be assigned. That was added in 2017. It was agreed in 2017. And before this agreement took place, because of the nature of Ethereum, once you deploy a contract, that contract's supposed to live forever. So if you would have in like 2016 before this agreement just used a opcode because the opcode hasn't been assigned at that time and used it as like a feature to abort, imagine that like maybe 2 years down the line from there, the opcode you have used gets assigned, and then suddenly the semantics of your contract change. That's why it was important to agree that there would be this opcode, the invalid opcode, which never going to be assigned. It seems like a tiny thing, but without this, the way to actually abort, and the only way to abort in a failing manner at that time, was doing some weird stuff like jumping to an invalid destination. And if you look at old Solidity contracts, they actually had like a special function, like a special pattern for this. And in the same update, the Byzantium, so still in 2017, the other interesting opcode to abort anything, revert, was added. So I think that was like, again, really important in order to have the ability to have some kind of error handling in their reporting. Because before that, we had this option of jumping to an invalid location. The only thing you get is all the gas is used, and that's it. And then invalid was the same, but at least you didn't have to use workarounds. But with revert, it allowed two improvements. Suddenly, it wasn't using up all the gas, and you could also return some data. You can imagine that before this opcode, it was kind of impossible to actually understand, what is going on without tracing. And at the time, there were some discussions to change the return value of call from the 0 and 1 to include a value for revert. The proposal was that the value 2 would be signaling that the revert took place. And the reason this didn't happen, because call is kind of like weird. It returns 0 and 1. And what does 0 and 1 actually mean? It is a Boolean. So 1 means true. Or is it? Goddamn! I kind of forgot. Is it 0? Is 0? Yeah, I need to look up the discussion, but the issue is that if this would have been added, likely some contracts would have broken. And this is already in 2017. It was really hard to make changes to the EVM. It was already riddled with existing contracts. And whenever you try to make an improvement, the first question was, what will be breaking after this change? Luckily, we were able to add like shifts, which I think were first proposed in like 2016 or 17. They were added in 19. And before shifts were a thing, the way to emulate them was with the exponential function. And that was actually repriced, I think, once, and it was extremely expensive. And I believe 2019 was the last time when a significant EVM-specific improvement went live. Most of the improvements relating to the EVM weren't originating from the EVM itself. They were originating from other system changes. And of course, one or like a number of changes which were beneficial to like users were all these different attempts to price storage changes, more fairly, which includes basically net gas metering, where the idea was that you wouldn't charge the storage change fully every single time, because you wouldn't actually write to disk the change until the end of the transaction. So any intermediate changes would or should be cheaper. And NetGas metering went live. It had its own issues, and then a second attempt was with the, I don't remember what is the name, but it went live at the same time. Access lists were introduced, and that version of NetGas metering seems to be okay. But all these different rules are like extremely complicated in an EVM. Okay, the last 2 points going to be much simpler. I just wanted to give you some background where to find more information on this. Of course, the yellow paper is like a good source of information. If you're interested in not the latest version of the EVM, because the yellow paper takes forever to get updated. I think the current version maybe, it is not the complete specification of Berlin, but I think most of the EVM stuff relating to Berlin is in there. And since then we had London and now Paris. Even though Paris doesn't really have too much of an effect on the EVM, the only effect it has is that the difficulty of code had like a rename and the semantics of it has changed. Beyond that, there are not too many changes in the EVM, but London had a number of them, and the yellow paper doesn't have those changes merged or even written yet. However, whatever exists in yellow paper is very nicely documented. There was an attempt to create a alternative version of this because it has been like a constant struggle over how readable the yellow paper is. And to some people, it is readable. To many others, it is kind of complex. It definitely has a large number of symbols, and it doesn't really have a glossary for these symbols. So one has to go back and forth insane amount of times. An attempt to solve this was the yellow paper, but I don't think it actually ended up being too successful. And I would imagine now, as of this year, EVM.codes would be the number one resource. People would just use to look up instructions. It is a great resource. It definitely has everything accessible easily. But if you want to get down to like the core of the semantics and all the edge cases, the yellow paper is a much better source. And then all the other changes kind of took place in like two locations. The EIP's repository is the main place where well-formulated changes to the EVM, and not only to the EVM, but Ethereum in general, the execution layer of Ethereum. But EVM changes definitely are formulated as EIPs. So that is the number one resource to look for EVM change descriptions. But it is a large repository of ideas, and it is extremely hard to judge in what stage a given idea is. The only way to judge that is by looking through all core devs and figuring out, what is being slated for adoption. Some of that is actually documented in this execution specs repository, which has, for each of the protocol upgrades, has a file with basically the different stages of proposals. They're like different. I think they even put it into different places, but the first stage a proposal would have to go under is called CFI, which is considered for inclusion, which only means that the all core devs group is kind of satisfied that this proposal is important enough to be considered, and they should spend more time discussing it. But it doesn't actually mean in like the early stages of that the group, which basically includes client teams, are looking into the specifications deeply. It may only mean that they're discussing it, 5 minutes every 2 weeks on the Allcodev calls. But once there's like a stronger decision, they're going to put it into the protocol upgrade spec, which is just a file in that repository, and they have status labels on whether it is implemented in any given client or not. And once it's implemented in multiple clients, one can be rather sure that the feature is more likely to be accepted, and it is something to be considered for language developers and security researchers. And then lastly, the active discussion is taking place on Ethereum Magicians, where people are floating ideas what they would like to have. EIPs also have to link. Each of the EIPs have to have a discussion URL, which mostly is on Ethereum Magicians. So each of these proposals have a discussion thread. Obviously, those which are under this like CFI, considered for inclusion, those going to have a lot more discussions than others. And the last topic I wanted to cover, and I just really want to give enough time for questions. I think we still have enough time. But I wanted to give you an overview of different EVM implementations, because there is at this point like infinitely many of them. And as you can imagine, this is not a complete list. But I wanted to give you, an overview so you can get started and do your own research into these. Number one, we of course have the different consensus clients. Well, pardon me, we cannot call them consensus clients anymore, because we have execution clients and consensus clients, and consensus clients refer to the beacon chain clients now, and the execution clients are the ones running the EVM. So these clients, I listed a number of them. This isn't a complete list, but the major ones today are kind of like Go Ethereum, Nethermind, Besu, and Aragon. Each of them have their own implementation of the EVM. Aragon branched off Go Ethereum. So the EVM implementation is very similar, and I think they even take the changes from upstream. But Aragon, as I mentioned earlier, they were the pioneers of the flat database model. So the rest of the client is significantly different to Go Ethereum, but the EVM, I believe, is still very similar. So these are like the main client implementations. These are the ones which have to agree, and everything else here doesn't actually, as of today, have to like agree with them, because if they have a failure, that's your problem. It's not the problem of the network. But kind of like an important one for everyone is Ethereum.js, which is a JavaScript implementation. And at some point it was, obviously it's used by a lot of the browser implementations. And at some point it was also used by MetaMask. And one feature all these browser implementations and wallet implementation used Ethereum.js for is running a transaction and getting like a gas estimate in order to set a gas limit for a transaction. The second use case is doing any kind of reading, like view or pure functions. So reading state. So this would be like the ideal case when we would have like light clients, and we would have most of the execution on the browser and the client side, and we would be sufficiently decentralized. Of course, this is not the case anymore, and we rely heavily on centralized services for getting data from. So I think like the significance, at least on the client side, may have, due to like, the shift to like centralized services may have reduced Ethereum.js's usage, but I think it's going to come back, and they're actively maintained, and they are actually the ones running a DevNet called Shandong, which for the upcoming like Shanghai protocol upgrade, they're running a DevNet which contains some of the features which are under discussions in Oracle Devs. So I think it's an important client to talk about. EVM1, where I'm kind of talking home, it is part of my team. It is a C++ implementation and is actually used in Silkworm, which is a sister project of Aragon. But it is also the implementation we use to prototype ideas and do benchmarks and benchmarks on. And then we also used the successful ideas from EVM1 and added them to Go Ethereum in order to speed up the EVM implementation in Go Ethereum. So it serves its place, but it's not really used in the network today. One implementation I think many of you have used is REVM, which I believe was actually inspired by EVM1, but obviously EVM1 is C++, so it's not really fancy. And REVM is in Rust, and so it can be used in Foundry, and that is the VM used in Foundry for all the tests. And I use Foundry, I like it. So of course, a lot of you have used it. What I'm trying to say here is it would be nice for REVM to get more eyes on it, because we depend on testing. And if the VM used in testing has actually bugs, then what are we testing against? So REVM is like a really important client in that sense. And I also forgot to mention that Ethereum.js is used in the same manner in testing. It is used in Truffle and Hardhat. So Ethereum.js and REVM are more important than you may think. And then an interesting one here is this EVM JIT, which it is a defunct project, but it was an attempt at writing a just-in-time compiler, which means taking EVM code and translating it into machine code, and then executing machine code instead of like an interpreter. Because everything else here, mostly, are interpreters. They just take each instruction one by one and try to execute it. It is rather slow. EVM JIT is one exception. It was written like in 2014-15. The idea was that this is going to be a way to scale EVM execution. It didn't turn out to be successful. There are also a bunch of like EVM implementations on other chains. It turned out like EVM OS on Cosmos actually just uses Go Ethereum. They don't have they just use Go Ethereum. That's it. But Aurora and Neon, they use Rust. They don't use REVM. They use a VM called Sputnik or a variant of it. There have been like 4 different versions of Sputnik, which was the VM used by Ethereum Classic, or like one client in Ethereum Classic. The 2 interesting ones on the bottom are HEVM, which is a Haskell implementation. And that is the VM using DevTools, and DevTools was like the inspiration for Foundry. So whoever used DevTools may have used HEVM. I think it has like interesting debugging features. Some others are missing. And then KEVM is the K framework implementation of EVM, which basically equals the yellow paper, the Jello paper, this one. Because this is just like a HTML rendering of KEVM, and KEVM has annotations. And then lately, of course, we have 2 different major ZK EVMs. And I only listed these 2, the PSE/Scroll and the Polygon/Hermes ZK EVMs, because these try to take EVM bytecode and execute EVM bytecode without changes. Many other projects who use the ZK EVM term, they actually translate EVM bytecode or Solidity code into something else and then execute that. But these 2, they take EVM bytecode without changes. So these were like the 7 different things I wanted to mention. And I think it took longer than I expected, but I'm happy to take the questions now. Pablo, help me out. Where do I find them?
I am here to help you out. And in fact, also post them. Let me pull your tongue while I'm doing that. Okay, so what is your, or maybe because we're security experts here, right? And some people were wondering like if it's possible to exploit the EVM and what are some of the security issues or attack vectors that exist.
I mean, if you find a new attack vector, then you should be claiming, one of the bounties. Just go to bounty.ethereum.org and report your finding. That being said, there are definitely areas where there's more risk, but we also need to define what are we interested in here, and risk on what level. So there's definitely risk in terms of differences between the different clients, and if such a difference is found, that means that you can split the network. However, Go Ethereum has a over 70% market share, so the only way you would be able to cause a bigger issue if you find a bug across different versions of Go Ethereum, which have a large share of the network, each of them, which is a hard case to find because it means that you need to find a bug in the last 3-4 releases of Go Ethereum. If you find a bug in a client which is used in a smaller percentage, then what you can achieve is you can split those clients off the network. So basically, you can just kill them. But that's the risk today. Now, finding bugs which would affect contracts and contract interactions, I think that is much harder. So finding differences between clients, there are different ways to do it. You can fuzz the different implementations, you can manually look at them. I think it's easier to find bugs between those, but finding bugs which would cause a problem for contracts, I think that's much harder. However, the third category is finding mispricings in different opcodes, and so you can definitely abuse the EVM, and there are many potential cases for that today.
All right. F. Tulligan has another question here in the chat. And it is what are any significant known differences between the EVM implementations that we should be aware of?
I finally found the chat. Significant differences between the different EVM implementations. I mean, as I mentioned, there was this attempt to do a just-in-time compilation. That doesn't exist anymore. Although I heard that some people are trying to do that again, maybe on some other chain. But there's no, at least not in production. And then EVM1 had two different implementations. In one case, it would pre-calculate gas costs for basic blocks instead of calculating gas on every single instruction. I'm not sure if there exists any other VM which does that in production, but I see Pavel on the call, so feel free to jump up and say if there's any such implementation. However, I did hear that some people are trying to work on parallelizing EVM execution for speeding up syncing. And obviously, such a EVM implementation would be rather different.
Okay, hold on, folks. Apparently, Pavel is typing. So in the meantime, Alex, what's your favorite opcode?
That's a good question. I think it's easier to say which ones are bad or like, complex.
Okay, Alex, which are your least favorite opcodes, and give us a reason why for all of them. For each opcode, why is bad? We don't have
all
enough
of them.
time for that, but give us tell us one.
Yeah, I mean, obviously, I like revert because it enables like all this error handling. What we have. I like static call because that's like one way to ensure separation. Yeah, I don't like. I mean, obviously, I like shifts because I was part of like introducing it, but I know that people dislike the swapped ordering, so I'm kind of maybe signing up to that sentiment. Of course, self-destruct is annoying, but the proposed version of like send all, like the new version of self-destruct, where you wouldn't destruct, you wouldn't remove the account, but you would still just transfer value with that execution. I mean, that terrifies me. I would say self-destruct today and self-destruct tomorrow. Those both are terrifying opcodes.
Hi everyone, I can quickly jump on the question that I had. So yeah, EVM1 was doing like fancy gas calculation, like doing groups of instructions during analysis and like summing up the gas cost of that block. And the idea came from actually EVM JIT. But there was some appetite to do the same in Go Ethereum, but even in EVM1 we actually ditched the idea because just the analysis cost of doing this is pretty significant. And like if you do it without it, but still like be efficient, it's the difference in the performance is not so big. Like partly because if you check like average EVM code, there's actually lots of branches in it because like mostly the code is doing some checks, like checking preconditions, all of that, and yeah, so it mostly checks some stuff and then do some stage modification, and that's it. So yeah, so mostly like this new interpreter within EVM1 that doesn't do it, and it's faster than the old one, so kind of we stopped doing it, partly because not so much time you can like evolve all of the ideas, but yeah, that's the current situation. So I don't think there's something really fundamentally improving the EVM performance. So yeah, idea is there, but not really improving over time.
Gotcha. Thank you for that. So, Alex, I believe Leastwood had a very interesting question, and it was about the thought process in researching and implementing new opcodes. So, how does that work, and what are the main bottlenecks in this process?
Yeah, I would say first of all you need like an inspiration what kind of feature you're missing, and that can come from like different reasons. Some opcodes come from need of like dev developers, and I think the growing optimizing gas optimizing community is also like a good source for ideas what would be useful or missing. Another reason opcodes come up is from trying to improve or change something in the broader Ethereum system. and that may have an effect on the EVM itself. But first of all, you need an idea what is missing or what would you like to change. And then second, you would need to properly describe, the change or the new feature. And the way to do that is like this EIP process. I mean, simply specifying that is likely the simplest way, the simplest part of all of this. But then it needs to be implemented in different clients. You need to benchmark it. You need to make analysis in terms of like the cost, analysis in terms of what kind of risks it can have. So there's a lot of like analysis involved. But the most important one is, understanding why you would want to have it and what other options are there today. And if the sole improvement this makes is just a slight gas improvement, then the likelihood of the change going live is very low. So there needs to be more motivation behind it than just improve the gas by 1%. Like a rule of thumb has been, is it making like a 10% improvement in the given feature compared to what you can do now? If it's less than 10%, it's definitely not worth even discussing it, because it's gonna be shut down. So it has to be a significant improvement if it's really only about gas. Yeah, I think that's really it.
Gotcha. And actually following up on this one, Riley had a question that also Dev Tooligan is adding on. So what are your thoughts on the transient storage or removing self-destruct?
Yeah, you're putting me on the spot with this like transient storage. I think transient storage
opinion, folks. It's only Alex's opinion.
Yeah, I mean, the transient storage has a really active discussion going on as of like yesterday and today on Ethereum Magicians. There are interesting, different sides of the discussion there. I think purely from a dev developer perspective, I probably would like it. Because it saves gas, right? And if I'm a dev developer, what I'm concerned about is mostly gas savings. And then secondarily is security, because the most important one is it has to be cheap, right? So from that perspective, I definitely like it. From the perspective of like a language developer, it definitely complicates things. And from the perspective of like an EVM person, it definitely adds another layer of complexity. Which I think has to be reviewed as well. And then regarding self-destruct, I would say self-destruct itself was like a neat idea, because it would be like this self-moderating community of let me delete what I don't need anymore, and this will help us keep the chain, tidy, and the state growth would be limited. As good as an idea it sounds, it actually never worked like this. It was abused with gas tokens, or from one side, from the client developer side, who tries to ensure that the system is feasible and the state is not growing crazily. They would say that it was abused. From like a dev developer perspective, it was a neat use case that you could save gas. So there's always like multiple sides to this, right? But the removal of self-destruct really comes from a different change, which, I mean, there have been like multiple motivations, but the big motivation is that self-destruct itself is unbounded. So whenever you self-destruct an account, all of the different storage items it has have to be removed. And this is an unbounded operation. So client developers are really concerned about this because it may not be well priced. But also this other change to overhaul the entire tree, which is currently the Merkle Patricia tree, and change it to Workle trees. The Workle tree system wouldn't really deal well with deletions, or at least the current version is really optimized to not have such account deletions. And so removing self-destruct will also help it tremendously. So the discussion of self-destruct really comes from these bigger changes in client developers.
Alex, we heard a lot about gas, and you just mentioned gas right now. And one gas-related question for our gas optimizers here, it's about Huff. So what's the deal with Huff? How does it relate to the EVM? And why is people so Huff-pilled lately?
Yeah, I think it's actually a super relevant question because I talked also so much about precompiles and how well or not well they are priced. And an interesting one is EC-Ed and EC-Mul. Because that's the history of Huff. So Aztec, which is a ZK dApp for private. Well, yeah, I think initially it was really for private transfers. They of course heavily reliant on EC-Ed, EC-Mul, EC pairing, and it turned out at the time, I believe this was in 2018 or 19. At the time, the pricing of the precompiles were such that you could write the EC-Ed and EC-Mul cheaper on the EVM using Edmod and Mulmod. But writing it in Solidity, of course, would be super expensive because Solidity is a higher level language. There weren't any widely used assemblers at the time. Writing it in Yule was also kind of not optimal because Yule at the time already didn't have low-level access to opcodes. So what happened is they wrote a macro language, which kind of looked like, at least in the original version, kind of looked like a C preprocessor assembly language. They wrote Huff in order to be able to write this EC-Ed and EC-Mul implementations in EVM, and they used it in production, and that saved them a lot of gas. We haven't talked about gas so much, but basically what Huff is, it is a really simple macro language, which lets you control, code generation quite clearly, and things like Yule and Solidity don't really let you do that. Yule does to a certain extent, but not to the extent Huff does. But I would also mention that this other assembler, ETK, also has a similar macro language or some macro features. So that is also something to check out. But yeah, Huff has a really great community, and more importantly, people are really into finding interesting ways to save gas, and they come up with really interesting algorithms. Something that's a great source for other languages and other tools and projects to learn from.
All right, we are literally out of time after this 55 minutes of intense EVM knowledge. So before we let you go, Alex, thank you very much for coming. We know that you're a busy person. So when EVM 2.0?
Hopefully this decade.
Hopefully this decade. Well, you see, folks, this is positive news. You can tweet that out. That's probably going to make a new bull run on the market now. So thank you very much. Thank you very much, Alex, for your time. And thank you all for tuning in and coming. All this will be posted on YouTube, and we will obviously ping you all. Thank you, Alex.
Thank you all.
Thanks, Alex.